Okay, this is problem 15.3. It's on page 664. A ceiling fan starts from rest with a uniform angular acceleration of alpha equals 0.8 radians per second squared. After 2 revolutions of the fan, determine the magnitude of the acceleration at point P on the tip of one of the blades. Okay, now in the figure, they give the distance from the center of rotation out to point P on the blade as 0.6 meters. But there's something else that they gave us. They said there are 2 revolutions of the fan. What kind of symbol should I put with revolutions? What is that? 2 revolutions of the fan. So what kind of thing is that? What is a revolution? It's an angular coordinate, isn't it? It's not omega. Omega is the speed. How about theta? There's 2 revolutions, so it's a position thing. Does that make sense? It's not the rate at which that position goes by. It's how much is accomplished. So there's a change in the angular position of 2 revolutions. Another way we could write that, if it's 2 revolutions, wouldn't that be 4 pi radians? So there's the change in position. Now, they told us something very important. They said that it starts from rest. How should I write down starting from rest? What should I use? 0. Okay, what is 0? What symbol do I attach to this? Omega naught. The initial angular speed is 0. Good. Now we're supposed to find the magnitude of the acceleration of point P. Now let me draw point P. I won't draw all, well, I guess I'll go ahead and draw the other blades. And basically this is the pivot point on ground, but I'll just leave the ground pivot off. So here's P. P is moving after the 2 revolutions with some tangential velocity. Now we're supposed to determine the magnitude, let's see. Yeah, the magnitude of the acceleration. What kind of acceleration would point P have? It has a tangential velocity, so what kind of acceleration would it have to have?
Radial velocity.
It would have to have a what?
A radial velocity.
A radial velocity? Well, if it has a radial velocity, it's going to fly off the tip of the blade. So I don't think there's a radial velocity. But acceleration, what acceleration would it have?
Normal acceleration.
Normal, there we go. There would be a normal acceleration, right? So I need to know the velocity after the 2 revolutions so I can figure out the magnitude of that normal acceleration. Okay? So let's do it. Let's figure out the velocity. How would we do that? Well, we've been given an angular acceleration, a change in position, and an initial speed. Are there any equations? Notice time was not given. Are there any equations that manage to deal with these things that might give us, it won't give us the tangential velocity, but we might be able to find the angular velocity at that time, which we could relate to the tangential velocity, right? Because we've already discovered the tangential velocity is equal to r times omega. Right. So if we had omega, we could get the tangential velocity without too much trouble. And then we could say the normal acceleration is vt squared over rho. And as I derived a moment ago, that would simply be omega squared r. So really, we don't even need to go through the tangential velocity to do this. We really just need the angular speed. So is there any equation that will give us the angular speed?
Omega squared.
There we go.
Equals
Omega squared equals
omega naught squared.
omega naught squared plus,
2a.
how about 2 alpha
2 alpha. Tan
delta theta? That's it. This equation should tell us the angular speed after the 2 revolutions or the 4 pi radians have been accomplished. So let's plug in the numbers and see if it does. So omega naught, 0, no point in even writing it down, plus 2 times alpha. Alpha is 0.8 radians per second squared, multiplied by delta theta. I'm going to use radians, 4 pi. Okay, otherwise my units won't come out the way I want them to. So I need some calculator help, please. Basically, we have 8 times 8 well, times 0.8 would be 6.4. I need 6.4 times pi, and then that will give me radians per second squared, which will,
20.1.
I'm sorry, how much?
20.1.
20.1.
1.
And then if I want omega, I'll have to take the square root of that. Right, so simplifying this, 6.4 pi.
4.48.
4.48, thank you. So 4.48 radians per second.
Wait, how much?
Anyone second that, 4.48? Okay. Now you might look at this and say, well, wait a second. You kind of played fast and loose because you got radians per second squared here. Where'd the other one go? Well, I forgot, 4 pi, this is radians. And so this really is radians squared, so in fact we get radians per second. But radians are one of those units that you can put in and take out anytime you want. It's a dimensionless unit, which seems strange, but that's what it is. Now are we done with this? Well, we got omega, why don't we go and get the normal acceleration? Get rid of this part, we don't need it anymore. So the normal acceleration, omega squared, I guess we could have just left it as omega squared, right? So that was, what did you say, 20.1 or so? Radians squared per second squared multiplied by r. R is the distance out on the blade, and that was 0.6 meters. Okay, so multiply 0.6 by 20.1, what do we have? 12.06. And that would be meters per second squared. See any problem with this? Where the radians go, like I said, they come and go at will. You don't need them, you just cross them off. Okay? I know you may be a bit uncomfortable with that, especially if you've just gotten a little bit more comfortable with units. You guys know me, I push you to use units all the time. But radians come and go whenever you need them to, so there we go. Who says you can't get anything for free? Are we done? We've got the normal acceleration, that's the acceleration of point P in this direction. Is the tangential velocity changing? Well, wait a second. This equation is still true. Vt, the tangential velocity, is omega times r. It's the angular speed multiplied by that distance, r. We know this is changing. We just calculated it after two revolutions, but it keeps increasing. If this keeps increasing, then this keeps increasing. That means this is changing, right? The tangential velocity is changing. That means there must be some tangential acceleration, right? So how do we calculate the tangential acceleration? I wrote down the equation a minute ago on the board. Do you remember what it was? How about this one? The tangential acceleration is alpha r. It's an easy one. So all we need to do to calculate the tangential acceleration is to multiply the angular acceleration, 0.8 radians per second, by the radial distance, r, 0.6 meters. And I'm sorry, that's radians per second squared. So 0.8 times 0.6 is how much? Well, 6 eighths are 48, so I think that'd be 0.48, wouldn't it? I did the math right? Now, which is the higher acceleration, the normal acceleration or the tangential acceleration? Obviously, the normal acceleration is quite a bit larger, right? But there is still tangential acceleration. So if I were going to try to draw this a little bit better to scale, let me get rid of the tangential velocity. I'll draw the tangential acceleration here. I'll have to draw the normal acceleration, something like this. The total acceleration would be the vector sum of these two. So here's the total acceleration of point P. It has a tangential and a normal component. If I had space, I'd shrink them both down so they weren't going over center, but I was trying to emphasize the relative size of those two. So how can I calculate the magnitude of the total acceleration of point P?
Square root of something.
Square root of the sum of the squares, right? So at squared plus an squared square root. So do it. What is it? I'm running off the video, so I'm going to erase this. Basically, we need to take 12.06 squared add it to 0.48 squared, and then take the square root. Of course, it's going to come out very close to 12.06, but it'll be slightly higher. 12.07 sounds reasonable. There's the total acceleration of point P. If you wanted, you could figure out the angle here or here, whichever one you want, so that you know the direction of that vector.
That's
But-
the acceleration of point P at 4 pi radians.
At 4 pi radians, good point. In the next instant, if this keeps accelerating, it'll be even higher. In fact, which would go higher? The normal or the tangential acceleration? Or would they both change? Well, the tangential acceleration is just proportional to the distance and the angular acceleration. The angular acceleration is a constant, the radial distance is a constant. So the tangential acceleration will remain constant. The normal acceleration will increase because the tangential velocity is increasing. So do you see what's happening? Initially, how much normal acceleration is there at point P when it's not rotating? There's none, because there's no tangential velocity. So all of the acceleration of point P is in the tangential direction. So if you're riding on the blade, you would see the acceleration of point P go from here and very quickly get longer and longer and longer until it's approaching a pure normal acceleration. Of course, there's always some tangential component, but it would just get longer and longer and longer in this direction. Of course, eventually it'll all fly apart like the windmill we saw, right? Because eventually the normal acceleration is so high that the force required to keep that mass connected to the rotating center is too high. And you saw the catastrophic results when that force goes up so high, the material can't hold together anymore. Any questions?